Your page took 410 milliseconds. The origin used 74. Where did the other 336 go? What if the origin has no request ID? This is path 001 from a typed URL to useful pixels. We will expose every boundary, reuse state, inject failures, then diagnose a changed trace. 1 request. 1 defensible answer. Start before the network. The browser separates scheme, host, port, path, query, and fragment. HTTPS selects security expectations. The host needs an address. The path and query identify the HTTP target. The fragment usually stays local. Interview shortcut. Call it the URL. Production answer. Each part changes a different decision. If the wrong product loads, prove the parsed target before blaming DNS or the server. Next, ask what the browser already knows. A reusable HTTP response can end the trip early. A DNS record can remove lookup. A secure connection can remove setup. A service worker can change the path entirely. Path 001 has 3 misses, so we take the cold route. Same URL, different state, different trace. Before debugging the network, identify which local state was eligible and whether it was fresh. The browser has a name, not a destination. A resolver returns address records and a lifetime. Path 001 spends 38 milliseconds here. That answer says where to try. It does not prove the application is healthy, the peer is authentic, or every user sees the same address. Here is the interview boundary. If the edge has no request ID, DNS and connection setup remain suspects. Start with evidence before the first server log. Now choose how bytes travel. This worked trace uses TCP, TLS, then HTTP. HTTP3 may use quick and combine those boundaries differently. Do not memorize one browser implementation. Preserve the questions: which peer, which reusable state, which loss behavior, and where security begins. We choose TCP here because the state changes are easy to see. The destination address is ready. A connection is not. TCP setup creates shared transport state, SYN, SYN-ACK, ACK. Roughly 1 round trip later, path 001 has an ordered byte stream. It spent 46 milliseconds. Connected does not mean completed. The application can still time out, reject the request, or return the wrong answer. This distinction matters in interviews. Transport explains delivery behavior. It does not prove business success. Keep the claim narrow. TLS turns that transport into an authenticated encrypted channel. The browser checks the expected host identity, and both sides derive keys. Path 001 spends 52 milliseconds before HTTP can flow. The padlock is useful, but narrow. It does not authorize the user, validate input, or make the application correct. A malicious request can travel through perfect encryption. State the guarantee precisely. Protected in transit to an acceptable peer. Now the browser sends a structured HTTP request. GET describes retrieval. The target carries path and query. Headers carry host, accepted formats, cookies, cache validators, and trace context. Path 001 connects later evidence. TLS protects sensitive headers in transit, not after termination. The interviewer follow-up is simple. Which field changes behavior? Name it. Do not hide method, resource identity, credentials, and metadata inside the phrase the request. The first server may be an edge, CDN, or reverse proxy. It can terminate TLS, enforce limits, check cache, select an origin, and add trace context. Our edge sees path 001, misses cache, and forwards it. This boundary has separate logs and ownership. A request can fail here without entering application code. Ask which server received it. Then, show the exact record. Architecture labels are not evidence. The origin routes path 001, checks authorization, waits for capacity, calls a product cache, then queries the database. Queuing takes 8 milliseconds. The database takes 41. The origin total is 74. That number is a dependency graph, not one block called server time. A healthy process can wait behind work. A fast handler can depend on a slow database. In an interview, decompose the total before proposing scale. The response separates status, headers, and body. 200 says this HTTP exchange completed successfully. It does not prove the price is present, the content is fresh, or the user can interact. A semantically broken page can arrive with perfect protocol success. Record status, body size, and cache policy separately. The production answer keeps protocol outcome and user outcome apart. That is how you avoid false confidence. HTML arrival is not the finish line. The browser parses it, discovers CSS, JavaScript, fonts, and images, then performs style, layout, and paint. Some resources repeat DNS, connection, HTTP, or cache decisions. Path 001 reaches useful pixels at 410 milliseconds. A missing style sheet can break the page after a 200. A long script can block interaction after paint. The user measures the experience, not one response. Run the same navigation again while state is valid. DNS and the secure connection are reused. Origin work remains 74 milliseconds because the product response still runs. Total time falls from 410 to 269. Nothing inside the application improved. The path changed around it. This is why isolated server averages mislead. When latency drops, identify which boundary disappeared before crediting a deployment. Now inject 3 failures. Slow DNS. The user waits, but the edge has no path 003. Redirect chain. Each server is fast, but the browser performs another request. Slow database. Setup is normal, then one dependency span dominates path 005. The symptom is the same. A slow page. The evidence is different. No edge record points earlier. Multiple request IDs reveal redirects. One long span points inside the origin. Locate before fixing. Real traces come from several systems. Browser timing covers navigation and rendering. Resolver tools cover address lookup. Connection diagnostics cover setup and reuse. Edge logs prove the public endpoints saw path 001. Application spans show queuing and dependencies. Do not subtract timestamps from unrelated clocks and call it truth. Prefer durations measured inside one system. Correlate with identifiers and ordering. Every number needs a source and a limit. Use the worksheet on any request. Give each boundary one row: input, output, time, evidence, and failure question. Then add your diagnosis, confidence from 1 to 5, one confirming signal, and one signal that would falsify it. This matters. Self-assessment is not guessing and checking the answer. It is making a claim that evidence can defeat. The diagram may change. The method survives. Checkpoint. The second navigation is 120 milliseconds faster. HTML and origin spans are unchanged. Which state was reused? Pause now. Write exact boundaries, confidence, one confirming signal, and one falsifier. Resume after committing. A strong answer names the DNS record and secure connection. Then checks lookup timing and connection IDs. Score the exact boundaries, confirmations, and falsifiers. 6 of 8, with no generic cache answer, is ready to defend. You can now defend one web request from URL to pixels and keep every guarantee narrow. Keep path 001 and your worksheet. Reuse them on a real slow page. Next failure lab. Retries can take down a healthy system. Now that you can locate one request, we will show how many reasonable requests amplify into an outage. Same rule, trace first, then choose the fix.